Actually, we got a gander at some beguiling pictures as the James Webb Space Telescope peers back toward the start of all that. This telescope has uncovered a revelation that challenges the preparations of our appreciation, enchanting the interest of room specialists and analysts. This divulgence shows a conceivably Goliath event, ready to do changing the universe as we currently see it. The significance of this finding is critical, raising stresses over the real reason for our self-important presence. The request arises. Might this revelation anytime lead to the uttermost furthest reaches of all that we know? Is the universe very nearly an uncommon event, beyond our continuous getting a handle on? Go along with us as we jump into the latest divulgence from the James Webb Space Telescope and investigate its possibility reshaping our appreciation of the universe. Our trip starts with an evaluation of the unmistakable universe. Our window into the huge domain, beyond the noticeable universe, consolidates all that we would have the option to distinguish, measure, and take a gander at with our telescopes and space missions. It is an assortment of stars, universes, and heavenly bodies obvious to us, tending to just an immaterial part of the entire universe, a little piece of a tremendous, limitless question that individuals endeavor to study and comprehend. Notwithstanding our movements, the general size and construction of the universe remain a secret. The width of the observable universe is surveyed to be around 93 billion light-years. This astonishing figure results from different components, including the distance light can go in 1 Earth year. The age of the universe, estimated at 13.8 billion years since the Big Explosion, surmises that the distinguishable universe extends 13.8 billion light-years in each bearing from Earth, inciting a distance across of, in any case, around 93 billion light-years. That's what Hubble's guideline exhibits. Space has been reaching out since the Big Bang, inciting the discernible universe. Moreover, expanding current measures suggest that light, released 13.8 billion years ago from a good ways of 13.8 billion light-years, is as of now approximately 46 billion light-years away. This augmentation suggests that the recognizable universe expands more than 46 billion light-years toward every way from Earth. The boundless turn of events, started by areas of strength for billions of years ago, has not only prompted the universe developing, but also accelerating. Astonishing forces, for instance, bewildering dark energy, appear to be driving this speed up, extending the universe's limits further apart. As the universe broadened, gravitational powers pulled particles together, prompting terrific structures like stars, cosmic systems, and planets, remembering our own Earth for show. In spite of the vastness of the universe, mechanical degrees of progress have allowed individuals to continually examine a more prominent measure of the universe. Specific telescopes, counting the Hubble Space Telescope and the James Webb Space Telescope, have engaged the impression of faraway stars and universes, making these wonders more accessible to the general populace. In thinking about the cosmic field, it is interesting to observe that even within our expansive nearby planet group, the universe appears strangely void. The nearest star, at whatever point scaled back to the size of a quarter, would still connect with 2 soccer fields far away. This immensity grows just inside our Milky Way galaxy, one of billions in the detectable universe, offering us a brief look into the massiveness of grandiose size. As we continue with our examination, the new disclosure by the James Webb Space Telescope adds another layer of interest to our perception of the universe, inciting further questions concerning the possibility of our presence and the potential for historic events on an endless scale. You might be intrigued by why we can't see the entirety of the universe. There are a couple of clarifications for this limit. Despite light being the fastest object in the universe, it still requires time to go through space. In this way, when we notice faraway objects, we are essentially investigating the past. The farther a thing is, the more its light has branched out to reach us, making a sort of gaudy time machine that unravels the verifiable setting of our universe as we witness worlds millions, if not billions, of light years away. Another urgent variable at play is the advancement of the universe. Imagine the external layer of an expanded inflatable material in specs. As the inflatable fosters, the spots move apart. Similarly, grandiose frameworks float away as the surface of space broadens. This expansion achieves an idiosyncrasy known as redshift, where the light created by far-off objects undergoes a change, and frequencies are expanded toward longer rosy tones. A couple of wonderful bodies, at last, beat a critical distance, showing up at the grandiose horizon, where their light is unreasonably far away to reach us due to the ceaseless improvement of the universe. Considering these two fundamental considerations, the development time of light and the improvement of the universe, it's not bewildering that we haven't seen the entire universe yet. Even with the most high-level telescopes and technology, our vision remains constrained by the essential components of the universe. We ought to dive further into these thoughts. The size of the universe is a moving evaluation in light years to show the distance light goes in a year. Our universe, the Milky Way, goes around 100,000 light-years. Even within our cosmic system, the closest star to our Sun, Proxima Centauri, is generally 4.24 light-years away. When we investigate space, we can see cosmic systems billions or an enormous number of light-years away, allowing us a brief look into the early history of the universe. The mystery of the universe's edge has enchanted the interest of individuals from various fields. While definitive plans remain unpretentious, three enormous speculations have emerged. The first suggests that the universe is immortal and enormous, with no obvious endpoint, expanding consistently in all directions. The second proposes a restricted universe without a conspicuous edge, similar to a colossal round or twisted space. In this present circumstance, traveling endlessly toward any way would ultimately take one back to the starting point, like circumnavigating the Earth. The third speculation, the multiverse theory, presents the chance of our universe being one among many, each with specific genuine standards. Furthermore, these universes might work openly or be interconnected, molding a gigantic and confounding multiverse. Examining these speculations sparks both sensible and philosophical interest. The possibility of a ceaseless universe challenges our perspective on space and its immensity. On the other hand, a restricted universe without an edge challenges our contemplations of limits and movement, proposing the potential for repetitive models within the surface of space. The multiverse speculation, with its parallel universes, opens up potential results beyond our current understanding, suggesting areas very different from our own. Anyway, it's critical to take note of that these thoughts remain speculative and interesting, requiring further assessment. Examining the universe's edge presents huge challenges, making it hard to totally endorse or dismiss existing theories. The boundlessness of grandiose space, combined with the limitations of our observational instruments and mechanical development, creates barriers in loosening up the secrets surrounding the constraints of the universe. At any rate, amidst this galactic weakness, the James Webb Space Telescope emerges as a sign of trust, promising to uncover insights into the bewildering beginning stages of our universe. The James Webb Space Telescope stands apart as a game-changing instrument, offering unrivaled precision in surveying the universe. This fascinating instrument has the potential to uncover the dark history of our universe, providing insights far beyond our current understanding. As a technical wonder, the JWST has recently made profound discoveries, particularly in examining the universe's edge. One of the astonishing discoveries includes the identification of 6 massive cosmic systems, dating back between 500 million and 700 million years after the Big Bang. Published in the journal Nature, this assessment challenges spread-out speculations about the origins and development of universes in the early universe. Incredibly, these old systems show widths far larger than expected for their age, testing estimates and altering the record of endless advancement. In defiance of starting suspicions for seeing infinitesimal youthful systems, astronomers were astounded to find these gigantic grandiose substances. The advancement of these outdated grandiose frameworks is stunning, comparable to our third 1-billion-year-old Milky Way universe. The stars within these enormous behemoths have an endless total mass, with certain infinite systems possibly having a grand mass up to 100 billion times that of our Sun. The JWST's unequaled ability to uncover the universe's secrets is laid out in its use of infrared light, imperceptible to the human eye. This limit engages the telescope to recognize faint releases from old stars and frameworks, revealing grandiose extras that have endured for billions of years. Acting as a time machine, the JWST sends our vision back through the ages, providing significant pieces of information into the universe as it existed around 13.5 billion years ago. The new discovery of huge frameworks, named universe breakers, has vexed our cognizance of endless progression. These astonishing revelations challenge the previously held models, investigating the standard belief that universes started small and progressed consistently over time. The James Webb Space Telescope, with its high-resolution photos and spectroscopic methodologies, has played an essential role in loosening up the secrets of these colossal universes, outperforming all presumptions. The possibility of very massive black holes lying beneath these systems adds another layer of mystery to the cosmic surface. In any case, when considering only a fourth of the information, the known mass of stars in the universe may now rely upon a dazzling multiple times more than past checks. This disclosure prompts a significant reassessment of how we could interpret enormous mass and plan with each new discovery, adding to our vast guide and offering a more detailed picture of the universe's arrangement of encounters. The out-of-control improvement of these huge cosmic systems offers important suggestions, representing our perception of how cosmic elements progressed from their initial beginnings to their cutting-edge shape. The James Webb Space Telescope challenges our overall approach to how cosmic systems can advance. This revolution in our understanding reshapes what we know about the universe's history and its complex structures. The data revealed by the James Webb Space Telescope pushes the boundaries of modern astronomy and forces us to reconsider our preconceived notions about the universe's early years. The discovery of these enormous, ancient galaxies suggests that galaxies could have formed and matured much faster than previously thought, adding an entirely new dimension to how we look at cosmic evolution. One of the most astonishing implications of these findings is that they could change the timeline of galaxy formation. The existence of large galaxies so early in the universe's history may imply that the processes involved in their creation were much more efficient and rapid than our models had predicted. Previously, it was believed that the formation of large galaxies took billions of years, but these recent observations suggest they may have formed in just a fraction of that time. Moreover, the discovery of such massive galaxies challenges existing theories about the rate at which stars were born and how they evolved in the early universe. These galaxies are not only much larger than expected for their age, but they also seem to be made up of a high concentration of stars, suggesting that star formation may have occurred at an extraordinarily rapid pace. This presents a new set of questions for astronomers. How did these galaxies amass such large amounts of mass so quickly? What forces were at play that could have accelerated the process of galaxy and star formation? The James Webb Space Telescope's ability to detect faint infrared light from these distant galaxies allows astronomers to see back in time further than ever before. By looking at light from galaxies that formed just a few 100 million years after the Big Bang, Webb is providing an unprecedented view of the early universe. The telescope's observations suggest that the conditions necessary for galaxy formation might have been present much earlier than we realized, possibly even as soon as the first few 100 million years after the Big Bang. Additionally, the discovery of these galaxies offers a glimpse into the formation of supermassive black holes, which are thought to exist at the centers of most large galaxies. The fact that these ancient galaxies are so massive and well-developed suggests that they may have been home to supermassive black holes from the very beginning of their formation. This raises further questions about the role of black holes in the early universe. Did black holes form before galaxies? Or did galaxies form around already existing black holes? Understanding the relationship between black holes and galaxy formation is one of the most exciting areas of current astrophysical research.